And Carolyn, the floor is yours.
Great. So it's a pleasure to introduce Joshua Krissansen-Totton today, who's a NASA Hubble Fellowship Program Sagan Fellow, kind of a mouthful, in the Department of Astrophysics and Astronomy at UC Santa Cruz right now. He specializes in modeling the atmospheric evolution of terrestrial planets with a focus on their prospects for habitability and potential biosignatures. So I think he's a really good match for the kinds of things we discuss in our group and in this seminar. He's originally, I believe, from New Zealand and went to the University of Auckland for his bachelor's degrees, and then completed a dual title PhD in Earth and Space Sciences and astrobiology at the University of Washington, looking at new exoplanet biosignature metrics and also carbon cycle models to better understand Earth's climate and evolution. For his postdoc work, he's looking at the atmospheric evolution of terrestrial planets, exoplanets, including the potential for non-biological oxygen accumulation on habitable worlds. So go ahead and take it away, Joshua.
Thank you so much, Carolyn, and thank you all for being here. So yeah, this work is done in collaboration with colleagues at UC Santa Cruz, other faculty, and also a number of talented students. So I'll try and highlight their contributions along the way. I am, of course, sorry I cannot be there in person. I have fond memories of visiting Austin when I was a very bright-eyed first-year grad student here, second from the left. It was one of the first places I actually visited in the US after moving to America. And so you got to understand, for someone who grew up in the South Pacific, only really been as far as Australia, Texas is like this quasi-mythical place. And so it was very exciting just to explore the city, and I had a lot of fun and hope to come back one day when it's safe to do so. So this talk is motivated by the expectation that our ability to characterize terrestrial planets is going to improve quite dramatically quite soon. So barring any calamities, and so this is a fun article in the Atlantic talking about the possibility of pirates intercepting James Webb on its way on the boat to its launch site. But barring any calamities, James Webb will soon be obtaining spectra of terrestrial planets. And so there's work by Caroline on this, looking at different assumptions about atmospheric composition, what, say, the TRAPPIST planets would look like to James Webb, and how you potentially you'd see quite large absorption features for different molecules and be able to characterize these atmospheres. A reasonable number of transits, so it's this is potentially quite exciting. And then, of course, there's the ELTs, which will be capable of similar transiting observations. And here there's a focus on how to sort of optimize the high-resolution spectroscopy so that you can detect molecules in terrestrial planet atmospheres with these telescopes. Looking further ahead, 3 of the 4 flagship missions currently under consideration by the Decadal Survey would be capable of doing quite detailed characterization of terrestrial planet atmospheres, particularly, especially looking for life. And so just to take LUFAR as an example, this instrument will be designed to be able to go after biosignature molecules present at essentially any time in Earth's history and be able to take quite detailed spectra to characterize the planetary environment. So all this is to say that the technological capability of looking for signs of life is happening in the near future. And so if we're going to be confident in our ability to identify the biological waste products of life, or indeed to confirm that life is in fact rare and that we've looked at all these planets and we haven't seen anything, I would argue that you need a quantitative understanding of the atmospheric evolution of lifeless planets. So there's a need here to couple the atmosphere interior evolution of planets to be able to do this in a way that is testable and comprehensive. And so with this kind of broad theme, this talk has 3 parts that have addressed this goal. The first part is looking at oxygen as a biosignature and its false positive, so applying these kinds of coupled models to oxygen to try and understand how it can be a biosignature and when it isn't. The second part, I want to talk about Venus and its application to highly irradiated terrestrial exoplanets and how that fits into the oxygen story. And then for the final part, and this is kind of more aspirational, but I think a similar approach can and should be taken to explore methane as a biosignature and false positives to methane as a sign of life. But we'll start with oxygen. So oxygen is, for a long time, before we even had confirmed the presence of exoplanets, people were talking about oxygen as a possible exoplanet biosignature. The argument for oxygen as a biosignature basically has two components. The first is that any life on a planet's surface, regardless of its specific biochemistry, if it can evolve oxygenic photosynthesis, and this will confer an immense selective advantage, and that it will no longer be, its energy metabolism will no longer be tethered to the availability of nutrients. And so this is part one. The second is that the geochemistry and atmospheric chemistry of lifeless but potentially habitable planets are unlikely to produce oxygen-rich atmospheres. So I'm going to take the first premise as kind of a given for this talk. I'm going to focus on how good this second assumption is. So there's certainly been a lot of work looking at photochemical scenarios for non-biological oxygen production. So here people, and this is by no means an exhaustive list of papers, but people have asked the question, well, okay, under different stellar spectra, under different assumptions about atmospheric processes and surface interactions, what are the circumstances under which you could potentially build up a lot of O2 photochemically without life? And what would be the clues that would let you know that that was what you were looking at? And so while this is still, I think, a work in progress, there's certainly a lot of understanding of what kinds of stars are more likely to produce oxygen, rich atmospheres, and so on. But there's a broader set of boundary conditions here that matter a lot for oxygen, the possibility of non-biological oxygen buildup that aren't often discussed. And so the likelihood of these sorts of photochemical scenarios depends on things like the bulk composition of the background atmosphere. How much nitrogen is there? How much CO2? How much surface water is there, if anything? And so these planetary boundary conditions can't be predicted from a photochemical model. They are a product of long-term interaction between the atmosphere and the interior. So this is really a time-evolving problem where, to understand the likelihood of non-biological oxygen production or non-biological oxygen-rich atmospheres now, when you observe a planet, it requires some understanding of both the astrophysical forcings, but also how the planet has evolved over time. So this is something I've been trying to model at Santa Cruz. And so this is our model. And I'll walk through it in a reasonable amount of detail because it's something we'll keep coming back to as the talk goes on. We start off with the terrestrial planet up formation, presumably in some magma ocean state, endowed with some amount of volatiles. And so you can potentially net oxidize your planet by dissociating water and losing the hydrogen to space, leaving behind the oxygen. And that oxygen, along with the other volatiles, will be partitioned into the magma ocean and the atmosphere and the growing solid silicate interior. Eventually, though, your planet will cool off to a more temperate state. You're still potentially net oxidizing the planet through hydrogen lost to space, but now you have all these crustal sinks of oxygen, processes that draw down oxygen from the atmosphere, volcanic outgassing, oxidation of crust, and so on. To model these processes, you need to, of course, track the energy budget of the planet. So modeling the convection of the magma ocean and later the convection of the solid silicate mantle. To track climate evolution, you've got to do the radiative transfer through the atmosphere. And of course, to do all of this, you need to know where the volatiles are. So it's also necessary to track fluxes of water and CO2, both as the magma ocean freezes, but also later fluxes of water and CO2 between the atmosphere and the interior through weathering and outgassing and hydrothermal processes. So I've sort of attempted to couple this all together to be able to tell one continuous story of terrestrial planet evolution from formation onwards, to be able to make testable hypotheses about their atmospheres. And this is by no means the only such model. There are other models out there that are doing similar things. And I think this was going to be really helpful to be able to do comparative modeling, because there's just so much complexity here that I don't think it's too complex to trust any one model. So with that qualitative description, it may make more sense to present some example results, and hopefully this will clarify how the model works. So this is an application of the model just to Earth without life. So here we're plotting the coupled atmosphere interior evolution of the Earth from magma ocean origins to 4.5 billion years later. This is log time on all the x-axes here. So this first panel is showing the temperature evolution of the mantle and the surface. This is showing the solidification of the magma ocean from the core mantle boundary up to the surface, a million years. The atmosphere is co-evolving with that. Crucially, the middle panel here shows you the energy budget. So this is showing the outgoing long-wave radiation as your magma ocean is cooling off. There's a critical transition here when the outgoing long-wave radiation drops below the runaway greenhouse limit. This is when the magma ocean freezes, your steam atmosphere condenses out as liquid water on the surface. So this subpanel here is showing you globally averaged ocean depth in kilometers. And once you have liquid water on the surface, a temperate carbon cycle can begin. And all the while, you're trying to track the redox evolution of the interior and the atmosphere to try and anticipate oxygen buildup. Now, what you see for this Earth through time calculation, I should say that, so the reason there are is a range of values is because you're Monte Carloing over everything you don't know. So all the uncertainties and escape processes, interior processes, we've tried our best to Monte Carlo over that, and that's why you get an envelope. But what you find is that after 4.5 billion years for a lifeless Earth, you always end up with no oxygen in the atmosphere. And so this is good news if you're interested in oxygen as a biosignature. It tells you that for a literal Earth twin, non-biological oxygen buildup doesn't seem very likely. And so even though there's all this complexity and unknowns in the modeling, this result perhaps reflects you don't have to solve all of planetary science to be able to answer questions about looking for life. That some outcomes seem robust to uncertainties in interior and atmospheric evolution. So that's the good news. The bad news is if you start to mess with the initial conditions, you can get very different outcomes. And so we have identified 3 sort of categories of planets where if you just run the story of Earth again, same planet-star distance, same star, but with different initial volatile inventories, you can get quite different atmospheres after 4.5 billion years. And so I'll go through each of these in turn. The first is this kind of eternal runaway greenhouse. And so here are the model outputs from that scenario. What's happening here is that you're endowing the planet with a high CO2 to water ratio in its initial volatiles. So what happens when you do that is the CO2 is almost all in the atmosphere. CO2 is not very soluble in the magma ocean. And so this ensures that once the magma ocean freezes, surface conditions are virtually always supercritical with respect to water. So water never condenses out as liquid water on the surface, even though you're at 1 AU. And so this means the mantle remains quite dry. There aren't a lot of volatiles in the mantle to subsequently be outgassed and draw down oxygen. Additionally, the high pressure from the CO2 atmosphere means what few volatiles are in the mantle tend to want to stay in the melt when you melt rocks. And so this further limits oxygen sinks. And of course, you have no liquid water for more than a very short amount of time. And so this limits hydration reactions. So all of this adds together such that you don't have many ways to draw down oxygen. And so a very slight leakage of hydrogen to space over billions of years is enough potentially to build up significant oxygen-rich atmospheres without life. You can see that in this figure here, where we're plotting final, so every dot is a model run, plotting final oxygen after 4.5 billion years versus versus the CO2 water ratio you started with. You can see as you push that slightly above the carbonaceous chondrite range, you can start to get this non-biological oxygen buildup. I don't think this is really a scenario to lose sleep over, though. These are not habitable planets. These are 100,000 bar CO2 atmospheres, no liquid surface water. I think there are observations you can make that would confirm this is what you're looking at. The second scenario is potentially more problematic. This is if you run the story of Earth again, but this time you endow Earth with tens to hundreds of Earth oceans worth of water. And so now when the magma ocean freezes and when that steam atmosphere condenses out, you're left with potentially hundreds of kilometers of oceans. And the immense pressure from this these vast oceans increases the solidus. So this has the effect of pretty rapidly shutting down new crustal production, shutting down melt production. And this isn't a new result. This has been documented in previous geodynamical models. But the redox consequences of that are that once you shut down crustal production, you shut down all your oxygen sinks. And so again, a very slight leakage of water to space, preferential loss of hydrogen is enough to build up oxygen on long time scales. And that's shown in this figure. Again, every dot is a model run. We're plotting final oxygen after 4.5 billion years versus the how much water you started with in Earth oceans. And you can see as you get several tens of Earth oceans, this potentially becomes a problem. So how might you distinguish such oxygen-rich atmospheres from genuine biological oxygen? The key really is to detect continents, because as soon as you can detect some kind of land-ocean dichotomy, that immediately puts a constraint on the ocean depth that would rule out these kinds of scenarios. So there are a number of ways you might be able to do that. Probably the most promising is time resolved photometry to back out a surface map and a land-ocean dichotomy. That might be the best way to kind of rule out this particular false positive. The final scenario is the opposite, where you start your planet off with very little water. And in this case, you get an interesting evolution where the magma ocean freezes quite quickly because you don't have enough steam to keep the surface molten. But the atmosphere remains steam rather than condensing out as water because you've got still a lot of heat coming from the interior. And so you have a narrow window over sort of a few million years where you've got a solid surface which limits oxygen sinks. So you can no longer mop up oxygen in the magma ocean. But you've still got a steam atmosphere, which makes it very easy to lose hydrogen to space and build up oxygen. And so you can potentially build up a few bar oxygen early on and hold on to that for a long time. And so this is work in progress done by a recent graduate, Max Galloway. Trying to get this movie going here. There we go. So this is just showing you how you can look at how the broader context, astrophysical context, can affect oxygen buildup. We're looking at atmospheric CO2, oxygen, and water for a bunch of planets. You can see the time evolving in the bottom left there. They're still all in the magma ocean right now. And so you can see once the magma ocean phase is over, as a function of planet-star separation, you start to see interesting trends in atmospheric CO2 versus separation, atmospheric oxygen versus separation. So where in that planet-star range you're most likely to get non-biological oxygen buildup. And of course, the time evolution, as you'll see now, as you get into several billion years, sorry, the last few billion years happened too quickly, I need to fix that. But of course, the star is getting brighter, and so you push more planets into this runaway regime, we potentially build up a lot of oxygen. So, as I said, this is work in progress, but the hope is that with such a model, you can do these sorts of calculations to try and anticipate and predict when non-biological oxygen accumulation is more or less likely. So to sum up that first part then, there may be ways you can make a lot of oxygen without life on habitable zone planets around sun-like stars. And so we've gone through 3 scenarios for how that might happen. Fortunately, there are probably observational discriminants that exist to be able to distinguish these cases from true biological oxygen. But taken as a whole, these kinds of calculations highlight the need for very generally capable direct imaging to be able to make the contextual observations you need to rule out these scenarios, do the time resolved photometry to characterize a land-ocean dichotomy and so on. And broadly speaking, habitable conditions plus oxygen alone is not, an unambiguous biosignature. So I now want to switch gears to talk about Venus for a while. And Venus is an important part of the story because Venus does not have an oxygen-rich atmosphere despite apparently extensive water loss, as evidenced by the elevated D to H ratio. So, it's a little strange that we have all these multi-billion-dollar instruments to characterize highly irradiated terrestrial atmospheres when there's this highly irradiated terrestrial planet right next door. We haven't attempted to fully characterize its surface and atmospheric evolution. It is literally the only other Earth mass planet we will have access to for in situ observations for, I don't know, centuries, maybe ever. And so I think it's understanding Venus's past is an important prerequisite to understanding these class of planets. So there's conflicting evidence on Venus's past. There's some exciting recent work done with GCM calculations showing that you could have had temperate climate on Venus until resurfacing quite recently. The way that works is the slow rotation basically allows for a lot of cloudiness at the subsolar substellar point, which creates a very high albedo, which could have permitted temperate surface conditions. There's also really interesting geomorphological evidence. There's my pointer gone. Okay, should be able to see that now. Looking at the oldest terrain on Venus, the tessera, where there are erosion features that some have argued at least to be analogous to fluvial features on Earth, that is flowing water carving out these features, although it's hard to rule out other aeolian processes, but it's interesting. The problem with recent habitability on Venus is that it's, if you want to argue that there's been a temperate past relatively recently, then it's difficult to reconcile that with the need to have lost the water and the lack of any leftover oxygen from losing the hydrogen. So to try and explore these different possibilities, we applied our model to Venus. This is the exact same model, really. We didn't have to tinker with it. We just sort of changed the planet size and made the planet star distance a little bit shorter. But otherwise, you just run the model as we did for Earth, and you can, in fact, recover the modern Venus state. So this is showing you reaching after 4.5 billion years, you can produce an atmosphere which is CO2 dominated with virtually no oxygen or water. You can recover the modern heat flow from the interior. I added a few bells and whistles like tracking argon-40 and helium as traces of cumulative outgassing and more recent outgassing. You can roughly reproduce the modern values for those as well, which is encouraging. And what is interesting, if you take all the model outputs that recover the correct modern conditions, there's this very clear dichotomy. You get these ones, which I'm showing in this figure, where Venus was never habitable. You just transition straight from runaway greenhouse to, rather, you transition straight from magma ocean to this runaway greenhouse, and temperatures have always been high. You never get a liquid water ocean. But there's also a class of model outputs that recover the same modern conditions, that is CO2 dominated, no oxygen, no water, but had a period of 1 billion years-ish of surface habitability where you condensed out about 100 meters worth of global oceans before returning to the runaway greenhouse phase and losing the water and mopping up the oxygen. And so the model can kind of reproduce this debate on Venus's past. Both scenarios are self-consistent. And this is just a zoom in showing those two differing climate trajectories, the one with the possibility of sort of 100 meters oceans. So you can then ask, okay, of these model outputs that successfully get you to modern Venus, what must be true of the parameter values you put in to get to this correct modern state? So that's what's shown by the small dots here. Again, every dot is a model run. The purple dots are model runs that successfully reproduce modern Venus that were never habitable. The yellow dots successfully reproduced modern Venus and had an epoch of habitability. And then the cyan, the blue dots, just fail to reproduce modern Venus. They leave behind too much steam or oxygen or something like that. And so some things are unsurprising here, right? This is showing you albedo of those different model runs. Of course, to make a habitable Venus work, you need to have had a relatively high average albedo. Both scenarios require relatively efficient oxidation of newly produced crust. So this is like a fudge factor I put in addition to outgassing sinks, what fraction of newly produced crust gets oxidized by any number of processes, whether it be direct oxidation of fresh magmas or explosive volcanism, oxidizing aerosols. Whatever that process is, the fudge factor needs to be sort of part per thousand. So you need efficient crustal oxidation. What's also interesting is that this subplot here is showing final atmospheric CO2 and final atmospheric water after 4.5 billion years. In addition to the model runs that successfully recover Venus, there are other possible outcomes that Venus didn't realize. Outcomes where a steam atmosphere was retained, or indeed where habitable surface conditions persisted until the modern. So I think understanding why Venus landed where it did, and not these other possible endpoints, is an interesting question and something that terrestrial exoplanet observations could shed light on. I don't want to spend too much time on this, but there is something potentially interesting here in that for any of these scenarios to work, you need comparatively high temperatures in the upper atmosphere. Otherwise, escape fluxes are too low. And so if you run the calculations again, and you assume that having a very CO2-rich upper atmosphere radially cools the upper atmosphere and throttles water loss, you find that you actually need to have had a habitable time to get rid of all the water. Because if you have this transient billion years of habitability, you can draw down all the CO2, store it in carbonates, and then more easily use your water to space because it takes time for that CO2 to build up again subsequently. But this is very sensitive to escape parameterization. So I'm not sure if I fully believe it, but it is interesting. But broadly speaking, though, both transient habitability and never habitable histories can be reconciled with the modern constraints, that is the bulk atmosphere composition, the argon-40, the helium pore, and the surface heat flow. So, and with the caveat that transient habitability is favored if you believe that CO2-rich atmospheres really throttle escape. So, understanding, it's kind of a frustrating result. I was hoping that with this fully coupled model, we could shed some light on which scenario was definitively more probable, but it seems like more in situ measurements are required here. And so understanding why Venus's atmosphere is oxygen-free is going to require better understanding of escape fluxes and just characterization of the atmosphere and the surface. And so in the paper on this we're working on, we kind of outlined some things you could look for if there was indeed 1 billion years of 100-meter oceans on Venus. you'd expect that to leave behind a lot of salt, halite, and hydrite, evaporite deposits that should be pretty substantial and something you could look for in the oldest regions of the crust. So as you can probably gather, all of this is working towards trying to come up with a predictive framework for terrestrial exoplanets that can take advantage of the comparative planetology opportunities offered by systems like the TRAPPIST-1 system. Presumably, all these planets are subject to the same stellar evolution, and so with a coupled atmosphere interior model applied to whatever atmospheres these planets happen to actually have, you can start to break the degeneracies in atmospheric evolution processes. And if you see a lot of non-biological oxygen on these interior planets, that tells you something about the likelihood of biological oxygen on these temperate or habitable planets. So that's work in progress. I think I'll just skip over this. So this is a summary figure from one of Vicky Meadows' review papers on oxygen as a biosignature, outlining all the different, these are largely photochemical scenarios for how you might make oxygen without life, but you can imagine broadening this framework with sort of a coupled atmosphere interior modeling approach. You can try and map out all the scenarios in which you might build up oxygen and the various observational diagnostics that distinguish those from true biological oxygen. So this is the goal. Of course, it's possible, though, that even if life is common in the universe, that oxygenic photosynthesis might be rare, or even if it isn't, that it's difficult for oxygenic photosynthesis to make oxygen-rich atmospheres. And so we definitely don't want to put all our eggs in one basket here. One thing you notice looking at the history of Earth's atmosphere, so this is the bulk composition of Earth's atmosphere as best we know it from 4 billion years ago to present. One thing you notice, other than the rise of oxygen, is that methane levels have been pretty high throughout, especially in the Archean when there was no oxygen around. And we think that virtually all of this methane was produced by life, by microbes. And so it's reasonable to ask, well, would methane on its own be a potentially useful alternative biosignature for planets that are like the Earth? And this has definitely been discussed for a long time. There are a number of papers exploring methane as a possible sign of life, but it's often disfavored just because there are ways of making methane non-biologically in some environments. But I'm not convinced this is a good reason to throw out methane in the same way that we don't throw away oxygen just because there are these processes that can make oxygen. It's just highlights a need for better contextual understanding. So some arguments in favor of methane as a biosignature. Like oxygen, there's a strong evolutionary imperative here for metabolisms that make methane. If you have CO2 and hydrogen around, and these are likely to be common substrates, common outgassing products, it's a very, it's sort of the obvious way to make a living geochemically, is to do methanogenesis. And it seems as though that methanogenesis evolved pretty easily and early on in Earth's history, and methane concentrations were likely high in Earth's atmosphere for most of its history, as we've seen. And from a more practical standpoint, it's just going to be easier to detect methane than it is oxygen or ozone, with James Webb at least, for sort of expected biological quantities of these gases. So this is something I've done a few calculations on. This is a simulated retrieval of TRAPPIST-1e, assuming it's got biological amounts of methane in its atmosphere, and it's pretty feasible, or at least it should be. A handful of transits, 10 transits, you can certainly detect the methane and put some crude abundance constraints on it. And you don't have to take my word for it. There are a number of other groups out there who have done similar kind of calculations, also showing that methane is pretty readily detectable with James Webb. There are even claims to have already detected methane on terrestrial planets. So this is a paper that came out a couple of weeks ago HST spectroscopy of GJ1132b. And so this is one of these highly irradiated terrestrial planets. I think it's something like 20 times Earth's insolation flux. And so they claim to have seen methane and HCM in the transit spectrum. I don't really believe these results for kind of theoretical reasons I don't want to get into now, but happy to discuss in Q&A if you're curious. But I think just the fact that people are already making claims about methane detections with current instruments suggests it's definitely going to be on the cards with James Webb in the near future. So with that in mind, there are, unlike oxygen, there is no coupled modeling framework to try and predict non-biological methane accumulation. This is certainly a subject where there's a lot of expertise. People in the earth science community think a lot about methane fluxes due to the importance for anthropogenic climate change. So trying to figure out exactly how much of the modern methane flux is humans versus other stuff. And also in the solar system context, people think about isotopic traces for biogenic versus non-biogenic methane with the hope of identifying life on Mars or perhaps the icy moons. But there's less focus on just how much methane can planets make on the whole rocky planets, and what would be the contextual clues for different non-biological production mechanisms. So this is something we've tried to start doing. I had a paper a few years ago looking at, well, making the case for methane in combination with CO2 in the absence of carbon monoxide, that combination being potentially compelling biosignature, and that methane and CO2 are out of redox equilibrium, they're separated by 8 electrons, and so it's difficult to think of non-biological processes that produce the two extremes in abundance without also producing intermediate carbon monoxide, which we don't expect to hang around in the presence of a productive biosphere because it's very easily consumed. And so you can kind of go through all the most obvious processes that might fool you into thinking you've found methane from life. The key point here, though, is that methane is, in addition to this thermodynamic disequilibrium, methane is kinetically, has a very short kinetic lifetime in terrestrial planet atmospheres. And so this is work done by Maggie Thompson, another Santa Cruz graduate student, trying to quantify this a bit better. But basically what we know is that abundant methane has a very short lifetime in terrestrial planet atmospheres due to its tendency to be dissociated, or equivalently, to maintain high methane abundances, you need very high replenishing fluxes from the surface. And so the question then becomes, if you see abundant methane, are there other non-biological processes that could generate large fluxes? So to work through kind of the obvious possibilities, UW graduate student Nick Wogan has explored outgassing sources, put together this model of CHO-bearing species outgassing, exploring a range of different mantle compositions, oxygen fugacities, surface pressure conditions, and basically showing that, lost my cursor again, but it's very difficult through outgassing alone to produce two extremes. Plants reducing enough to make a lot of methane also make a lot of carbon monoxide, and so you wouldn't really expect this if it was biological methane. Impacts are an interesting process that can certainly make methane transiently. So we've done some calculations here looking at, for different size impactors, what does the atmosphere look like evolving in time after that impact? And again, you can potentially make a lot of methane for a while, but it tends to be associated with high carbon monoxide abundances, and is also, in any case, going to be very transient just because of the short photochemical lifetime of methane in terrestrial planet atmospheres. There are a whole number of other processes that can potentially make methane: water rock reactions followed by Fischer-Tropsch type processes, metamorphic reactions. And so we're trying to quantify these as best we can. But even for Earth, these mechanisms are poorly quantified. The basic point, though, is that certainly for hydrothermal processes, even under very generous assumptions, it's hard to make more than sort of a few teramoles per year of methane by these processes compared to the many tens of teramoles per year, which is the biological flux of methane. So we think in sufficient abundance, it's going to be challenging to think of plausible non-biological processes to fool you into thinking you found life. And so just like for oxygen, where we had this framework of potential non-biological processes, we can hope to put together a similar kind of framework for methane, where we acknowledge that yes, there are a number of scenarios that make methane without life, but those are either going to be accompanied by a lot of CO, or the methane abundance isn't going to be very high. And so these are all contextual observations you can make to give you more confidence that we're in fact likely looking at biological methane. So to conclude, for the methane, atmospheric methane is perhaps the only readily detectable biosignature accessible to James Webb. And so we've argued that abundant methane in combination with carbon dioxide, but not a lot of CO, is hard to maintain without biology. Certainly for the most obvious mechanisms you might think could fool you. But this is not well understood. And so this is kind of a call to get people interested in methane as a possible biosignature, since it is observable imminently. Just to wrap up, I have hopefully convinced you that the search for life on exoplanets is pretty hard to separate from attempts to understand just the expected lifeless evolution of terrestrial planets. And so for that reason, having coupled atmosphere interior models to formulate testable hypotheses is going to be important for interpreting upcoming observations. Oxygen as a biosignature is definitely the best understood in this regard, but there are still a lot of things we don't know. James Webb observations of highly irradiated terrestrial planets are going to help with this understanding, just confirming whether or not they have oxygen-rich atmospheres would be immensely helpful, as would returning to Venus and understanding Venus's atmospheric evolution in more detail. And I'm hopeful that a similar approach can be taken to understanding methane as a biosignature, although currently the understanding of planetary processes is sort of lagging behind our observational capabilities. So yeah, that's all I had, and very happy to take questions. Thanks very much.
That's applause in our language here. I have one.
Oh, maybe if people have questions, they can either interrupt or raise their hand. If I see raised hands, I will call on you. Yeah, go ahead, David.
Just a quick and perhaps easy one. Does your model predict all our other planets okay? The ones that freeze out quite quickly?
This is a good question. I mean, I currently haven't built in the ability to do cold places. There isn't, things don't condense out. Water and CO2 don't freeze out, rather. And so it's something that could be built in principle. I'd like to explore Mars. Mars is complicated for other reasons, just its smaller size means you have to worry about larger things escaping. So yeah, currently it doesn't do cold planets, but it's something I'm interested in looking at.
Yeah, I was wondering if you'd used these coupled models to look at planets around M dwarfs as well as like sun-like stars, because certainly those are some of the planets we'll have more access to with James Webb. And I think, in my mind, at least, the astronomy community is really thinking a lot about atmosphere loss during the early lifetimes of those planets, which seems like it's a race between outgassing and losing the atmosphere. Have you looked at any of those questions yet?
Yeah, I mean, that was the goal from the outset. I was going to do the TRAPPIST planets and other planets around M dwarfs, and I kind of got distracted along the way with all these interesting things from the solar system. But that's the next step, is to do make some first order predictions for these planets, and then from that try and figure out, okay, what would you need to observe to be able to constrain escape, or is it hopelessly degenerate? I mean, the hope is that you can, with the comparative planetology of, say, TRAPPIST, you can use the similar stellar evolution to be able to constrain how some of these processes work. So that's working on that.
Yeah, sounds good. Other questions? I see Andrew.
Yes, thank you. Joshua, I really enjoyed that talk, so thank you. Thanks for that. I was just wondering, like in the case of like having a catastrophic event where maybe like a planetary impact occurring, in your modeling over time, how do you take that into account? Or is that basically you have to just maybe reset the system back to maybe time zero? I'm just curious about that. Thanks.
Yeah, so I guess if you're thinking like a giant enough impact to create a second magma ocean, then I didn't explicitly model that in these runs, but that would essentially be a reset with whatever volatiles you have at that point in time. Depending on how deep you melt the mantle, I suppose you could potentially retain some volatiles in the deep mantle, but that would be interesting to simulate what the consequences of that. I did do, so for the oxygen question, I was interested in whether adding impacts would affect the likelihood of oxygen buildup, because of course, if you dump enough reducing material, you could potentially stop some of the scenarios. And so in that case, I just did typical envelopes, what people think from heavy bombardment onwards. And it might inhibit the third scenario that I presented, where those desert worlds, we don't start off with much water. If you have a high enough impact flux early on, that could potentially draw down that few bar of oxygen you start off with. It doesn't affect the other scenarios so much because all the oxygen accumulation happens later on. I expect a similar thing to be true if you hit planets with larger rocks, like that'll mess things up early on, but kind of if you just have a very large water inventory, that's, once things have calmed down, that's going to have the same effect, suppressing melt production and potentially allowing for oxygen buildup.
Great, yeah, thank you, great.
Other questions? Tim, go ahead. You're muted.
Yes, I recognize that I'm muted. So I had another question about sort of like the dynamical evolution, whether you could put into your model dynamical reorganization of the planets. I'm thinking in the NEAS model, well, the NEAS model doesn't even have the inner solar system, right? It's all black box for the inner planets, but like one would imagine that the perturbations in the outer giants significantly affect the orbital parameters of the inner planets. And so I wonder if that's another thing that could be incorporated into your model, and whether those type of reorganizations, which I don't have a good intuition for how common they might be in other solar systems, but whether those might actually be important in terms of bumping planets' trajectories along your model outputs, right? If Venus is starting in one place, but then its orbital radius changes by 0.1 or 0.2 AU, might that explain why Venus ends up where it does?
Yeah, well, that's an interesting thought. It's certainly something that would be easy enough to implement, I think. Just changing the planet-star separation, evolving that in time would just be something else to impose. I haven't tried that just because I don't have the kind of orbital evolution knowledge to know what scenarios would be most pertinent. But that's certainly something I'd be interested in looking at, and potentially with exoplanet relevance there as well. If some of these planets around early M dwarfs have evolved in their orbits, that could dramatically affect their prospects for retaining volatiles.
Okay, are there other questions? Go ahead, Sean.
Yeah, I guess just to follow up on that, the tidally heated question, whether you've played around with, say, the same planet, that's in a tidally locked situation, and then one that's not, and how much of a difference that actually ends up making.
Yeah, since my focus has been on, can the Earth be different? I haven't explored the range of tidal heating values you might get for exoplanet systems where that might be a major term. I would say that for those oxygen scenarios, I am sampling a pretty broad range of, it's called radiogenic heating, right? But it could equally well be tidally heating. It's just a factor of like an order of magnitude range. So within that sort of range, it doesn't affect the scenarios too much. I mean, you get more melt production, more internal heat, so that tends to draw down more oxygen. But if you could get planets with more extreme tidal heating than that, then that could certainly affect the evolution. I guess the challenge is there. It's hard to know when you push things to really high tidal heating, like what that looks like tectonically, and where is the melt being placed, and yeah, very unconstrained, interesting questions, which matter for the oxygen question, because where that melt gets put matters for how easy it is to draw down oxygen.
Yeah, that's very interesting. Thank you. Great talk, by the way.
Thanks.
I guess related to that would be the question of whether your model with minor tweaking could account for moons orbiting beyond not around the primary, like the Jovian system, had it been Jupiter been a little warmer, for example.
Like if you place Jupiter in Earth's orbit and then,
well, let's say it had been just twice as massive or 3 times as massive, so we're still radiating, and keeping its moons warm.
I see. Yeah. Yeah, I mean, in principle, that's something you could do. There are so many interesting calculations I'd like to explore. Yeah.
Great, any other questions? I don't see any, so let's go ahead and thank Josh again for a really nice talk. That was really interesting. Thanks very much.
Thank you for the interesting questions and great suggestions.
Great talk.
Great, thank you.